Welcome, everyone. So we learned from the other session. We start really punctually instead of 6 minutes later, so
Yeah.
we made it.
We did made it. It's like 1 sharp. Where's the excitement? Like, it's 1 sharp. Thank you. Great you all made it back. Thanks for coming here. So up next, we have Torsten. And Torsten actually built wood frames for a living before he started actual programming. So please give him a very warm welcome.
Okay. Hi there, everyone. So, sorry, that was actually the wrong way around. I now build houses after I code, after I've been coding for a relatively long time. So, I'm going to show you quickly how it's possible to compile Ruby to binary. And this, I think, ties very nicely in with what Terence said. We shouldn't let anyone tell us what's possible or not. You know, everybody always says you need to interpret a dynamic language, and that's just not true. So I'll show you how. Just a little bit about me. You can find me, I'm not very social, but on GitHub you can find me. I've been coding on and off, you know, I'm not professional, but mostly I do it as a hobby now. So this for me is a project of passion, you know, I really love Ruby, basically. So I'm from Finland. That's a typical Finnish way of enjoying your time, which maybe may or may not be considered weird in other parts of the world. So this is ice, and then going into ice, yes. So I run a bed and breakfast with my wife in halfway, basically, between Helsinki and Finland. My wife came along, so we can have a little bit nice time. So so in 30 minutes, basically, you know, it's not difficult to compile, but it can go relatively deep. Now I'm sort of trying to find the balance between you getting an understanding that it can be done and not going too deep. But 100% Ruby, not too much of it, about 10,000 line of code. Yeah, I mean, like many have Rails projects that size, right? Well, if you check out Go or something, it's like much bigger. So like I said, I love Ruby and for quite a while already. And I'm hoping that this could be something of the many things that we've learned that the Ruby community brings into the larger community. Because dynamic languages, obviously we like dynamic languages, and the only thing they suffer is from speed, really. So I read, does anyone know Smalltalk here? How many? Yeah. I actually read the Smalltalk 80 in the 90s. I read it, made a big impression on me. It's actually quite like the Ruby implementation, just that Smalltalk's a little on the weird side, though. So, like I said, the main problem we have with Ruby and most other dynamic languages that where not big companies have thrown lots of time at it is speed. And I experienced this very strongly when I bought a Raspberry Pi the first time. I think basically Ruby makes a Pi out of my laptop and an Arduino out of my Pi, and it shouldn't. It only does that because it's interpreted, really. We have this results in this classically called two-language problem, that we have to choose between a nice language and a fast language, and I'm hoping with this that we don't have to make that choice in the future anymore. Okay, and of course with the Ruby that could be nice. So by compiling Ruby, we solve all the problems basically in one foul swoop. That's great. We get a faster we could get a faster implementation. We wouldn't have to choose anymore. And it's in Ruby, which I always call it the Rails effect, when when developers can change their own tools, then you get this super boost. You know, you go into warp speed. Boom. So just before going into the compiling part, we'll just a little bit go over basics. So any program I'm going to see like takes input, produces output, right? Okay. MRI basically takes your source code as input and produces output. So as a secondary input, but it is a program that takes your source as an input and interprets it. In compiling, we have two stages. So there's this compiling stage where with a hello world here, in C, we would take the source file, it takes it in, produces an output file. It's a binary, okay, and later we can run this, doesn't have any dependencies anymore, and it produces its output. So this one-stage process that we have in Ruby becomes a two-stage process, and that creates a little bit of problems then. So if we were to do this in Ruby, and we can, I can actually. So you create a hello world program, run run a compiler that I've written, and get a binary. This is possible with the code that I have created. And then you run this hello program, and it does its thing. With more difficult things, I'll show you later, it's not quite so easy. So that's just a refresher how it is with MRI. And if we wanted this behavior with a Ruby compiler, we would have to create a program that's called Ruby there, that when we type call Ruby, that is the output of another compiling process, obviously, in the MRI with all that C that they have. But we would have to have some code that is the compiler and compile that with our compiler, and then later run it when it can compile more. So that's where it gets a little bit, I don't know how many people got that actually. So basically we compile the compiler with itself. It's what any decent compiler, any C compiler will also do as a first step. That is how one would do this, and that's the sort of benchmark and where this project is going. Obviously it's not there yet, otherwise you would have heard about it before. So it's there is a fair bit working, I find. So these things I will go into in more detail, each of them. But basically sort of objects and classes are working. We have a calling convention that is not like the C calling convention. It's actually, you can actually understand it. I will have a slide about it. I'm hoping at least you can understand it. It's a very simple memory layout, and there is a binary creation process that's something I won't go into so terribly much because it's a standard. There's an ELF standard that tells you how binaries need to be laid out. It's a bit like digging into the HTTP standard or something. So things we have working are sort of basic control structures, if else, sort of basic things, while, like no breaks and continues, assignment. So a fair bit of a sort of basic. Sending, especially the static calling, doesn't happen so often, but it's a process, sort of the dynamic sending is a process of finding the actual method that you want to call then later, and then shuffling arguments and then actually jumping there. That all works. with a little bit of caching even. So that was good, I think. Even some blocks I got done last year. So blocks are in a way a little bit like sending, but different. So when you write Ruby, you have an implicit block. So we can actually capture that and pass it as an argument, as Ruby does, and then basically do a send, as it were, and return from that. So, and Ruby is a rather large language, of course, something we like about it. There are things that I haven't started, basically. It's not because necessarily difficult, but those basics had to be done first. Eval is basically compiling at runtime for us. It's not so difficult then. If the compiler would have compiled itself, it would run at runtime, and you would just basically compile at runtime. Doing procs completely right is a little bit more tricky, but exceptions, and I'll go into it later a little bit with the calling convention, is conceptually relatively easy, and with the right calling convention then shouldn't be so. Okay, I'm just skip over the rest. So the nice thing about sort of starting from scratch when you program a Ruby compiler like this is you can do everything new, and so everything is relatively simple. Everything is an object, Has anyone done extensions here or dug into the MRI code? That's not too many. Okay, a couple. So Ruby pretends that everything, or MRI, that everything is an object, but it isn't actually. In RubyX, it actually is. Every object is an object, and the data that is integers or strings is actually opaque to the Ruby in the compiler, and there's a lower level of built-in functions that can access the lower level data. So this Ruby implementation is then more about the actual sort of management layer. Okay, and how there's a large problem with this the dynamic nature of Ruby, which is why people have not done this before, I think. So you can change the class at any time, and so if you equate classes with types, it doesn't work. Types are not classes. Classes can change, and types cannot. For types, if you ever anywhere read anything about types, for that to be for the word to be meaningful, they can't change. So types are immutable. Every object has a type. This type never changes, but the type that the object has can change. So that's where we get that dynamic nature. So classes are represented by types at a moment in time, but as time goes forward, the class changes. A different type represents the class. And then one just has to manage changing these type references. So that was sort of the overview. Now the compiler is, of course, like any program, structured mostly in layers, where really the processing just falls down and down. So we start with a Ruby. There's luckily a parser gem that parses the Ruby code. First layer, then that's an untyped data structure that one gets back. So the next layer is basically a typed version of that, and slightly simplified. And then there's two sort of machine layers, what I call the minimal object-oriented machine and the RISC, before we go into actual binary creation. And ARM is the only implemented architecture at the moment. But it's relatively simple to plug another one in there. So I'll go through these layers a little bit, just so you get a little bit more idea, and then that's where the level of detail then stops. So the what I call the virtual, the VOOL, virtual object-oriented language, is a sort of intermediate layer I created, so one doesn't have to, one can remove the complexities of Ruby, like all these different ways of doing the same thing, which we like, but then that's a level where it's just one way of doing things. There's only an if, and there's no unless, and there's no splats, and all these other things that we have in Ruby. 3 ways of writing hashes, and God knows. So the next level down in our data processing are then machines, the machine layers. And they differ from language layers. Language, everybody I think is more used to. You have syntax trees, but machines have instruction lists. So things get linear. We have abstract concepts of maybe if and whatnot, but the machine has it's very pretty concrete. You know, it doesn't have control structures. It only has jumps. It doesn't have variables. It only has memory, and just sort of so you know what. Now we're jumping into the sort of first machine level, where it's an abstraction, of course. This one is just a little bit like the VOOL level. It's just sort of that one can go down and do the processing in sort of defined steps. You know, I started out trying to go from Ruby into binary. You know, you get brain problems. It really doesn't work. So it's relatively simple. Only has 16 instructions. They're relatively abstract. A couple of them to show you. The Ruby truth check is very specific. That is an instruction, so one can just go down in one, and then the next step then has to actually implement it, or an identity check, or a dynamic call is even an instruction. It's a relatively complex operation, but modeled as just one instruction at this level, as are other things. And then we go down into a RISC abstraction. This actually nothing to do with the RISC-V. It's just a reduced instruction set. Everybody familiar with that? Yeah. So ARM is a RISC implementation, so it's relatively simple to the ARM. But again, ARM has its peculiarities, and this is just a simple model, a simplified model of this ARM layer, basically just modeling the things that the compiler needs to create code. The ARM instructions then also blew up into hundreds and even thousands. But this is very small. I think the RISC-V, if anybody has followed that, they also they manage with 50 instructions, and at the moment we're still at 20. So it's a very small, understandable set of instruction that's and having this instruction actually allowed me to write an interpreter for it, which then again allows to test at that level, which is very, very handy. And then later, when I actually got into writing binaries, it's very difficult to debug binaries. You know, you get these core dumps and things. So I wrote a visual interface for the interpreter, so one can try and understand what's going on. And if we have time, which I think we might not, I'll show you. But it's online anyway. So the RISC instructions there then sort of about registers, moving data, and mostly basically pointers then in the good old C world. Around and loading and doing operation on them and very basic stuff. So, and from here to the ARM is mostly a one-to-one mapping. So it's very close for ARM, but then if one wants to go to Intel, I guess it's different. So now you sort of understand the layers, and I talked a little bit about the object model, and I want to talk a little bit about the calling convention, because these are sort of the code operates with the internal assumption of these things. You don't see the calling convention or the object model anywhere directly in code, but all the code in the code, it's implied how these things work. And then C, this is just not very easy to understand, and so it's part of the reason why it's I think difficult to write languages if one has this calling convention and you don't understand where the data is and what it does. So instead of using a stack, I'm using a linked list, and it's a linked list of objects, right? There's no just popping stuff onto random memory addresses or whatnot. So when you call a function, it says you create a new message, it's called, and then you just fill in the data, and it's really, and then so when you have to do exception handling, for example, then it just means it's a linked list. So you just walk the linked list to the catch, right? That's it. So it's not so difficult. Or bindings. Bindings are basically is the message that encapsulates what Ruby has as a binding. You can pass those things around. What? Yeah, exactly. You have so the actual object is very simple. These are the instance variables of the object. So you have the caller and the next message, the local and the arguments, return value and address, and the self. And it's just all very plain if you do it in an object-oriented language. It's like, yeah, of course. So just trying to demonstrate that programming in this environment isn't sort of black magic as one might think programming on a C compiler is. It's not. So and there is a third component. The standard lib, I call it parfait, is really thin a layer of for minimal runtime that the compiler already needs at compile time. Actually, so you have about 20 classes like the message and a hash and a string you need to actually start before you're starting, and then you have this little problem with the booting, but that solves that. And then you can write the standard lib completely as Ruby code, because there are, of course, like an integer multiplication or a string access or a file open. The things that Ruby cannot do. It's just not possible. So it has to be a different method, some different code to do this. So just briefly, so this isn't just an idea I had just yesterday. I actually had it at the Frozen. What is it called? Frozen Rails in 2014, I think. And I've been working at it ever since. And now I think it's sort of ready where I've gone through several architecture iterations. I've made my mistakes. I didn't know what I was doing, of course. Um, but now we have different. One could start with different CPU architectures. The plugin mechanism is sort of there. There are basic executables it generates. So I think it's ready for other people to participate, which is why I'm here. You know, I'm not here because, like Terence also said, any successful project needs a team, right? I think I've taken this as far as it needs to for other people to understand that it's a viable idea, you know. And if it's a if the community at some point doesn't think it's something we want to do, it's not something. I'm not going to do this on my own until it's a full Ruby implementation or so. So you can find this online at rubyx.org, or of course on GitHub. And we can sort of do one of two things. We can either take some questions, or I can show you this this debugger. And I think we'll do this way, that we'll do questions later. You just come and talk to me. I think, and I'll show you a little bit this debugger. So this is actually online here, online, right? On the so on RubyX homepage, you go to architecture, to debugger, and scroll down a little bit. It's there. There's a description on it, what this actually all is. But basically, you have some global objects here, also the classes here, and this is the risk level. So it's register. These are registers. And here's a way to preload some code. So I go here to hello world, and then it actually does it compiles. No, that's the little, no? So this is an Opal application. How many know Opal? Right? All the other ones, look it up. Opal translates Ruby code into JavaScript code. And the JavaScript runs, of course, in the browser. So this is since the RubyX project is 100% Ruby code, no external dependencies, Opal translates this into JavaScript code, which is visualized here. It's actually just 500 lines of code. So this is the first. Program starts at the first branch, and then we can single step through this program, and at every step, when it loads data into a register, we of course know that it's objects in the registers, and then you get a visualization. So here you have a message with all the data that I talked about, and next message. Oops, you can go actually and look at this data, huh? So that was really helpful to debug stuff, huh? And then you can go through, and you can go faster, and you can even faster. Yes, and we can see, for example, here that we have taken 87 instructions. Risk instructions now, right? And this is actually the standard output. Not surprising, it says hello world. And this is actually the return value. If you were to run this on the command line, you would get a return value of 11 back, which is the length of hello world. Right. So we have a minute for one question. But Yeah. Okay, let's take one. Yeah, I understand. So those would be. Okay, I repeat the question or what?
Yeah.
Okay.
Do you actually have some kinds of benchmarks, like compared to MRI, for example?
Yeah. Like I said, this is not a complete implementation yet, and so those would be micro benchmarks. I did some early on. I did a little bit when I was fiddling with the calling convention, and the actual calling convention is itself something like 50% slower than C. And everything else, I think, is actually due to how fast you would do it. And I think there's a good chance that you can get things, because you can compile at runtime. You know, you can measure and compile, recompile at runtime and inline things. I'm hoping one should be. It should be possible to get to at least twice as fast at C, or in parts, I think, as fast as C or even faster. But directly, benchmarks would be a next step now, yeah. But there's also many other things to do. So, as I said, I'm hoping somebody would join me here. Okay, I think that's it for now. Thank you, everyone.